Let's look at an example with some slightly different geometry and go through our process. We have a long rod with uniform charge density, and we'd like to find the electric field at a point P above one end. We'll go through our same steps. We'll identify one little element of charge. We'll call that dq. We'll draw the electric field at point P created by dq. Since our charge is positive, the electric field points away. This is our element of electric field, dE, and it has components, dEy and dEx. We want to write dEy and dEx in terms of dE, so let's identify an angle theta. And we know that dEx is adjacent to our dE, so it's going to be dE times cosine theta. dEy is opposite our angle, so it's dE times sine theta. All right, next we'd like to identify our parameters and write down what we mean by dq. So for our parameters, we've put our coordinate system so that x is horizontal, y is vertical, and we've put our rod so that the left end is at the origin. So here's our origin right here. X is our distance from the origin to our dq, so this is x, and x is a variable. Because if we pick our dq at different places, it will have different values of x. Y is our vertical distance from the rod to our point, and no matter where we pick our dq, we would have the same vertical distance. That means y is a constant. We're going to write that dE is k times dq divided by r squared, and r is the distance from our point to our element of charge dq. So here's r. So we see that r is the hypotenuse of a right-angled triangle where the legs are x and y. So r is equal to the square root of x squared plus y squared. What else do we need? We need cosine theta. Cosine theta is adjacent over hypotenuse. That's x over r. Sine theta is opposite over hypotenuse, so that's y over r. And last, we need to do our dq. We see that the rod has uniform charge density. Since it's a linear rod, it's one-dimensional, we use linear charge density lambda, which is the total charge divided by the total length. That means that the little bit of charge dq is going to be equal to the charge density times the length of our charge element. You see that our charge is in the horizontal, so the length of it is a little bit in the horizontal direction. It's dx. Okay, so the length when we have a horizontal rod is dx. Okay, we've got everything identified now. We're ready to put all of our terms together. So we've got r, we've got cosine and sine theta, and we've got dq. We'd like to figure out our x and y components. Why don't we get started with the y component? So let's write down what dEy is. dEy equals dE times sine theta. dE is k times dq over r squared. Sine theta is y over r. So we've got k, dq is lambda times dx. It's times y. We've got r squared times r on the bottom. That gives us r cubed. So we've got k times lambda. I'm going to swap the order of my dx and my y because I'm allowed to do that. And typically in a math class, you put your d whatever at the end. Y times dx. And then that's divided by r cubed. R is the square root of x squared plus y squared. And then that's all cubed, so something to the square root, which is cubed, is going to be the power of 3 over 2, just like we did in a previous example. So there's our expression for dEy. I don't have quite enough room to write dEx on this slide, so I'll go on to the next slide. We know that dEx is equal to dE times cosine theta. We'll fill in that dE is k times dq over r squared. Cos theta is x over r. So we've got k times lambda times dx times x over r cubed, which ends up being k times lambda times x dx over x squared plus y squared to the 3 over 2. Okay, so there's our elements of the x and y components of the electric field. The next thing we have to do now is take the integral to find the values of the components of the electric field. At this point, we might ask if any of those components are going to sum to 0. Is there any symmetry in this problem? I think maybe I'm not going to answer that right off the bat. You think about it, and let's see what the math tells us in the end. Let's find our y component now. So we'll remember that our net y component is the sum of all the elements of the y components. We'll fill in what we know for our dEy, which is k times lambda times y times dx divided by x squared plus y squared to the 3 over 2. We'll take our constants out in front of the integral. The things that are constant this time are k and lambda and y. The x is our variable, so everything with x's has to stay inside the integral. We're integrating with respect to x. That means our limits have to be from some x initial to some x final. When we do our integral, we go from one end of the rod to the other. So let's go from the left end, where x initial equals 0, to the right end, where x final equals L. So x initial equals 0, x final equals L. So we're going over the entire length of the rod because that's where the charge is, starting at the left end, finishing at the right end. Okay, what's our next step? So as always, you can either do this integral on your own or you can look up the result. Either is acceptable. When we look up the result for this integral, which is my method of choice, what we get is k times lambda times y, that's the stuff that's outside, times 1 over y squared, times x over the square root of x squared plus y squared. That has to be evaluated at x equal to L and x equals 0. First, we'll deal with this y a little bit. I've got a y in the numerator, y squared in the denominator, so we get a little cancellation there. We've got k times lambda over y. Those are all constants. They can sit out front. Then I'll put in my x equals L term. So I've got L divided by the square root of L squared plus y squared. Then I'm subtracting the term where I put in my 0. So 0 over the square root of 0 squared plus y squared. So this whole term is 0. So let's write this all together. What I've got is k times lambda times L divided by y times the square root of L squared plus y squared. Okay, there's our y component done. To find our total x component, we add up all the x bits, so it's the integral of dEx. Let's fill in what we have for that. K times lambda times x dx divided by x squared plus y squared to the 3 over 2. It's going to range over the limits from x equals 0 to x equals L, just like on the last slide. 0 to L. Take our constants out front, k times lambda. X is a variable, so that has to stay inside. 0 to L, x dx over x squared plus y squared to the 3 over 2. We can look up that integral in the book if we wish, and what we get is k times lambda outside of minus 1 over square root of x squared plus y squared. That's got to be evaluated at L equals 0. So we've got k times lambda. First we'll plug in x equals L. Then we'll subtract the term where we plug in x equals 0. And then we'll just write it nicely to finish. K times lambda times minus 1 over L squared plus y squared minus 1, I dropped a minus sign. There, I'll just put it back. minus times minus 1 gives us plus. 1 over the square root of 0 plus y squared is the square root of y squared, which is just 1 over y. Okay, now we've got our x and y components. To finish, we make sure we're comfortable with our signs, and then we write as a vector. Let's finish up our example now. We might notice here that neither of the components turned out to be 0, and that makes sense. For all of the rod here, no matter where dq is, the y component is going to point up. It's always going to point away. For the x component, it's always going to point to the left. So it makes sense that the x and y components do not turn out to be 0. We don't have any symmetry in this situation. We don't have things the same on top and bottom or the same on left and right. So it's okay that they're not 0. What about the signs? So if we look at our electric field, we know that all of the y components point up, and we know that all of the x components point left. So EY is up. It has to be positive. EX is left, so it has to be negative. Okay, so this is where we really have to use our physics sense to know the signs of our vectors. So now we'll finish just by writing our electric field as a vector. Our net electric field is going to be the x component. It points left, so it needs to be negative. The x component goes with an I hat, plus our y component. The y component is positive. And that goes with the j hat. So there's our total electric field above one end of a long rod.